Hi guys, let's start infinite limits. We're going to just cover the first three examples here for 1.5, and our main focus is going to be how infinite limits relate to vertical asymptotes, and we're going to take a huge look at our reciprocal function 1 over x. So for this first example here, we have our function equaling 3 over x minus 2. Well, this is really just 1 over x, our reciprocal function. It's being multiplied by 3, and it has a shift right 2. So a couple things to remember about your reciprocal function. You have a couple of asymptotes. One at y equals 0, so we'll go ahead and draw that in, and an asymptote at positive 2. Because we shifted. Normally it would be at x equals 0, but our shift right 2 moves that. Because we're multiplying by 3, instead of going over 1 up 1, we would go over 1 up 3. Okay, and then we can go over 1 down 3. Alright, we're going to have an intercept at 0 and negative 3/2, and then we have our two branches. Alright, now a couple things to think about with the branches. We had talked about when we were reviewing vertical asymptotes, if you have your linear factor to an odd power, the branches are going to be on opposite ends of your vertical asymptote. So even though this is the rational function, that same rule really applies. Okay, what we're going to do next is we're going to take a look at what happens as our x gets closer and closer to our asymptote. Now visually, we can already see that this is going to decrease without bound, this is going to increase, but we're going to take a look numerically because it's always nice to have a wide variety of approaches in trying to figure out those limits. So if you had your calculator out, you would plug this into y1 equals, you would go to your table, plug these guys in, and you're going to get negative 6, negative 30, negative 300, and negative 3,000 as our values get closer and closer to 2 from the left side. All right, so obviously on the graph we can see it's going to decrease without bound, but you can see as we get closer and closer to 2, you can see a huge difference between these values and how as we get even closer it's going to continue to be even smaller and smaller values of y. So then if we're looking at 2.5, so now we're going to come from the right hand side. 2.5, we have 6, when x is 2.1 it's 30, 2.01 is 300, 2.001 even closer is 3,000. So again, as we get even closer and closer to 2, those values for y are just going to keep increasing without bound. All right. Well, we talked about limits, and we said, hey, you know what? Limits are what a graph looks like. All right. It may not be what it actually is, but it is a nice way for us to describe what's happening with the graph. Okay. What does a graph look like when x is 2? Right. The issue is, in this case, when we have limits increasing or decreasing without bound, we would say the limit does not exist. And that is a true statement, and that is still true. All right. However, I want you guys to put a star next to this statement here. We're going to start describing our increasing and decreasing without bound using infinity. Now, we're using infinity as a symbol. That's it. Okay. This does not mean that this limit exists. In fact, infinity is not a real number. It's just a symbol to say that it's increasing without bound.